Tell me what the role of theory is in this space. And put it in the comments. I'm really curious what you have to say. This curiosity is piqued by my conversation with our guest, Alessandro on his paper, Learning Optimal Deterministic Policies with Stochastic Policy Gradients.
Thank you, Alessandro, for joining us to discuss your paper. We're excited to have you.
Thank you, Alison. I think this is an invaluable opportunity to spread my work to the scientific community, and I say thank you to you.
Yeah, so before we dive into your paper, I'm interested in your journey into the space. You did your bachelor's degree, your undergrad in computer science and engineering, focusing more on robotics, and then your master's, also in computer science and engineering, had more of a focus on artificial intelligence and machine learning. So what kind of drove that interest, and how did you end up in this field in reinforcement learning?
It all started about when I was studying for my bachelor. As you said, I studied computer science and engineering with a focus of robotics and automation. And then I switched for my master to another focus on artificial intelligence and machine learning. And in particular, during the machine learning course, my professor, that is Professor Metelli, told me about the reinforcement learning problem. That was actually the problem to learn to control something. So I thought that it was a perfect bridging between my bachelor and also my master. So I really enjoyed it. And my interest increased a lot during my master thesis that I've done on online learning, and in particular for application to automated machine learning. So I fell in love with this word, and I became very passionate about reinforcement learning.
And so that's, in your paper, you're talking about reinforcement learning. So tell us the motivation for this work, specifically the title of your paper, Learning Optimal Deterministic Policies with Stochastic Policy Gradients.
Practice starting from scratch. Reinforcement learning is, as I told before, a learn to control problem. So you are in a setting in which you have an agent that is interacting with an environment. And the goal is to learn how to behave optimally in each situation. So the agent actually is getting the state of the environment and is selecting the best action to perform each time. So this optimal way of behaving is called policy. And in practical scenarios and in real world scenarios, what you want to have is a deterministic policy, because all the theoretical works about reinforcement learning are actually investigating the learning of policy. But in real world scenarios, when you are deploying a way of behaving, actually, you do not want a stochastic object. You want something that is meeting some real world requirements that are, for instance, reliability, traceability, and explainability, and also safety. And this stuff is actually achieved by a deterministic policy. So the motivation actually is to try to meet some real world requirement with the theory.
Okay. And now I want to dig a little bit deeper into that problem space before jumping into your paper. You kind of mentioned there are some sort of limitations in deploying stochastic policies in the real world. Why are they so useful then in learning?
In particular, there are some works that are about learning deterministic policy directly, that are Deterministic Policy Gradients by Silver et al. 2015, a really good paper. And then it's the version, Deep Deterministic Policy Gradients. In this situation, we are just trying to give a theoretical groundings to what is actually done. So learning in a stochastic way, and then switch off the stochasticity and trying to say something about the performance of the deterministic version of what you have learned stochastically. In practice, in reinforcement learning, as we were mentioning before, you want to learn how to behave. So you have to explore, actually, the space of action. So when you are simulating in an environment your action, you want to try the most of the action. And you have two kind of ways to explore, and we will delve into the details later. But actually, you are introducing a form of stochasticity at two levels, or at the parameter level, or at the action level. And at the end of the learning process, where you reach the convergence at your stochastic objective, and then you want to deploy a real world policy, you cannot provide the consumer a stochastic object. So you have to switch off the noise. In this particular case, try to say something from a theoretical perspective about this practice of switching off the noise at the end of the learning.
Okay. And so that leads us directly into the
Okay.
paper, which is essentially a proof. It's a lot of math.
Yeah.
There's a lot of math.
Yeah.
But give us an overview of kind of how you formalized this approach and then how you evaluated that and your findings.
So starting from scratch, we introduced before what is reinforcement learning, and we introduced also the need for exploration. In particular, and during my PhD, I'm trying to identifying some real-world requirements to see if theory is actually able to meet these requirements. A key requirement, of course, is to have a deterministic policy, as we said so far, but also to deal with continuous action in state spaces. And among the reinforcement learning methods, there is a family of methods, the policy gradient methods, that are actually able to handle continuous state and action spaces. And moreover, they come with a lot of other benefits that meet real-world requirements. For instance, they have a lot of robustness to the noise of the actuators and the sensors that may have, for instance, robots, or they have a robustness for what concern also the partial observability of the environment. And moreover, they have a key feature that is the allowance to the designer of a policy to incorporate its domain-specific knowledge when designing the policy. In particular, policy gradient methods are actually learning directly the parameters of a parametric policy. And what is done is to plug the exploration at two levels here. So what has been always done in theory is to have an exploration at the level of actions. For instance, if we talk about a deterministic policy, that is a policy that, given a particular state, will always provide the same action. An action-based exploration approach is actually changing time by time with a particular noise the action that is provided by the deterministic policy. There is another approach to perform exploration, that is an exploration at the level of meters. So before you start interacting with the environment, you have your parameter vector of your deterministic policy, and you are changing a bit this parameter vector, and then you plug this changed parameter vector into a deterministic policy, and then you interact with this modified deterministic policy. This is called exploration. So these two kind of exploration are actually typical of two very famous algorithms that are GPOMDP, or reinforce, for what concern the action-based part. And these algorithms are actually old, let me say, because the first paper is about 1999. Instead, for what concern the parameter-based scenario, the algorithm is called PGPE, is very famous for what concern the practical applications, and it was published in 2012. In 10, sorry. So these two approaches are very used, are very famous, and what we did was actually trying to have a unified formulation in order to study the convergence guarantees of the two approaches. For what concerns the action-based exploration, theoretical analysis about it were carried out since the paper was published, actually, because action-based exploration has a way more theoretical flavor, and it is actually prone to theoretical enhancing. While parameter-based exploration was not investigated that much under a theoretical perspective, it was always been a more practical scenario. And indeed, there are a lot of works that are using parameter-based exploration for robotics or, for instance, autonomous driving. So what we are trying to do here is to, at first, make them converge in a unified framework, because, as I said, action-based exploration was a lot of explored in that direction. Why parameter-based not? And in particular, we provide theoretical guarantees of the last iterate. So we are actually saying something about the last parameter that is seen during the training phase. And we have last iterate guarantees for both the algorithms, let me say, to the global optimum. And then also we map the stochastic objective to the deterministic one. And we provide also last iterate convergence guarantees to the global optimal deterministic policy.
Tell me a little bit about the unified approach. What benefit does that bring into training?
In particular, the unified approach is something novel because we actually built up this unified approach, but not for an empirical stuff, but more for theoretical analysis. Indeed, we have in our paper this generic algorithm that we call exploration agnostic, because the proof works both for the parameter-based and the action-based exploration. And we are able, with that particular unified framework, to assess the last iterate global convergence of a generic policy gradient algorithms to its last iterate global convergence of its stochastic objective. Then, the fact is that you have to leave this unified approach when you want to have the guarantees on the deterministic policy, because another novelty of our work is that we managed to map the difference between the deterministic policy with a particular parameterization and the stochastic performance index with the same parameterization. And we find out that this difference is actually depending on new problem dimensionalities. Indeed, when you are talking about tabular environments, so environments with finite states and finite actions, what you have is that the problem dimensionality is the cardinality of the action space and also the cardinality of the state space. Here, since both state and action spaces are actually infinite, we have new problem dimensionalities that are, for instance, dimension of the parameter vector, the dimension of the action vector, and also the length of the interaction with the environment that is called the horizon of the problem. So here we can use the unified approach to converge to the stochastic objective. Then when we want to map to the deterministic convergence, what we have is that we need to use these rules. And here we have the new problem dimensionalities. So we can also enjoy the difference in the trade-off between the two exploration approaches.
Okay. And it's true also that in this paper, it is novel, your approach as it relates to parameter-based exploration and the global convergence guarantee.
The novelty of the relation with the parameter-based exploration is not the algorithm, as I told before, because the algorithm parameter-based exploration was published in 2010. It was a PGP. But the unique, up to my knowledge, at least, theoretical guarantee about parameter-based exploration policy gradients was published in 2011, and it was a first-order stationary point convergence. So last iterate global convergence is novel for the parameter-based exploration, and it is achieved thanks to this unified approach. The last iterate global convergence for the action-based scenario was already assessed in 2022. And the fact here is that we use to prove the global convergence an assumption this is called weak gradient domination. The weak gradient domination is actually resembling a lot of cases, a lot of settings that were already analyzed in other paper about action-based exploration. And here we have that, long story short, we are requiring that the objective function the algorithm is trying to optimize has a local optima that is far until a certain distance. Okay. So this particular weak gradient domination can also be inherited by the stochastic objectives when it is assumed on the deterministic objective. And in particular, other paper found out that if you are using particular kinds of policies, for instance, Fisher non-degenerate policies, then the weak gradient domination is actually generated by this is induced by this particular kind of policies. So we use these weak gradient domination, and there is an entire section in our paper that is discussing about it to ensure global convergence. And actually, this assumption required us to develop new technical tools that are of independent interest that actually were needed to get at the end of the proof, actually.
Okay, and I want to go back a little bit to the evaluation. How did you think about the trade-off between sample complexity and performance?
Okay. Actually, the sample complexity is the statistical complexity in terms of number of trajectories that are needed to ensure a certain degree of accuracy of the deployed deterministic policy. And in particular, if you want a high accuracy, then in this case, since it is last iterate, we are evaluating just the difference between the optimal value of the deterministic objective minus the expectation of the value of the deterministic objective evaluated in the last parameterizations deployed by our algorithm. If you want that this difference is small, up to an epsilon factor, you have a sample complexity that is very large. So the more you want to be accurate and the more you need samples, the more you need trajectories. If you do not want to be that accurate, so you can have a sample complexity that is not that big. But actually the sample complexity here is telling something more about the trade-off between the exploration approaches. Indeed, as our theory is suggesting, and it is not the first trade-off of this kind that we see between parameter-based action-based exploration, is that parameter-based exploration can actually struggle with highly dimensioned parameterization, while instead action-based exploration may struggle with long-lasting interaction. So when the agent is interacting a lot with the environment before starting a new trajectory, and this is because of the nature of the action-based exploration. Indeed, you are adding noise at each step. And moreover, the action-based exploration may struggle with highly dimensioned actions. And this trade-off is actually present also in the sample complexities that we have when we leave the unified approach and we see the sample complexities of the parameter-based action-based exploration, and also in practice with our experiments, it can be said.
So is that what you attribute the performance gap between, that you show in your paper, the performance gap between the action-based and the parameter-based to? Is that just a natural function of the way they work?
Yeah, in particular, the performance gap that we show in our paper is about when we are just changing the scale of the noise we're using. Is there any value of the scale of noise? In our particular case, we employed a 0 Gaussian noise. So is that any value for the variance of the noise that is enabling us to have a deterministic performance that is the highest possible? And in both the cases, the answer is affirmative. And what can also be seen is that parameter-based exploration struggles effectively, actually, with a highly dimensioned policy, for instance, neural networks. That can be a real problem in real-world application. While instead, the action-based exploration is struggling with long-lasting interaction.
Are there specific types of environments or problems where you would expect one method to consistently outperform the other method?
Okay. For a real-world usage or for some particular usage, I will I would see what dimensionality of the problem the method struggle more with. For instance, for what concerns the parameter-based exploration, theory is actually telling us that they struggles with highly parameterized policy. So if I know that a particular task cannot be solved without a neural network policy, I maybe would go for action-based exploration. Instead, when we are in front of a long-lasting task, a task that between the starting time of the interaction and the ending time of the interaction has a lot of steps, I would go for the parameter-based exploration, because our theory is saying that the error that we have in mapping the performance from the stochastic objective to the deterministic objective is depending on these two dimensionalities. So for P.D., they depend on the parameter dimensionality and how much noise we are using. On the other hand, for A.B., this mapping depends on the noise that we are using, the horizon we are facing, and also the action dimensionality. So I would make this distinction before deciding to go for one exploration approach or the other one.
Let's dive into the noise
Okay.
a little bit more. So the paper focuses on white noise-based exploration. How might your results change or generalize for other types of noise-based exploration or other exploration in general?
In particular, the choice of this kind of noise for us, so a white noise, so a noise with zero mean, and that hence has to be white between time steps for us, is crucial when you quantify the distance between the stochastic objective and the deterministic one, because we are exploiting the structure of the noise, how the zero mean white noise is done. Okay, so in this particular case, if we want to use a different noise, or we want just to use a different kind of exploration, we have to change these results that are the final results. So the one that allow you to change from the convergence to the stochastic objective to the deterministic one. We have to change this part, and maybe it is not that immediate. What we can do here instead is to play with the scale of the noise, because in our setting we select a scale of the noise and we have the noise scale constant during the whole train. At the end, we switch off the noise, and indeed we pay a term that depends on the variance value if we are talking about Gaussian noise. In particular, our theory is suggesting that there is an optimal amount of constant noise that we can use, but it is of order of the accuracy you want. So the theory is suggesting, okay, you have an optimal amount of noise to get to the optimal deterministic policy, but this amount of exploration should be very small. This is actually something that is making the learning time exploding, because if you are exploring not that much, you have to train a lot, and moreover, in practice, you may not find a good performance in the deterministic policy. So in practice, what you have to do is to search for this scale of the noise. This is a drawback, I think, and indeed I am thinking about how to fix this problem with an adaptive scale, for example. No spoiler.
That's a limitation. Okay. What's the future for this work, or what you're able to share? Anyway?
For this work, I think that we can go in two directions. The first one is super theoretical and is about to lower the rates of the sample complexity. There is a scientist that manages to do it with the action-based scenario, and I'm thinking about whether I can replicate the same with our unified approach. And from a practical perspective, in order to have a more usable algorithm for real-world applications, I think that changing the scale of noise is the key. I mean, or you have a schedule for the noise during the training step, or you have an adaptive scale of noise that is changing according to something. I'm working about it. I hope that you'll read about it soon.
I'm interested in training as it connects potentially to this rise in AI ethics and safety concerns. Okay. The AI Act for the EU, right? Banning certain kinds of applications on the market. I'm curious the relationship or the potential relationship that could have with training. Like, in your opinion, like, what are your thoughts on transparency in training methods, particularly for critical applications? Should there be mandates related to training methods?
This is a critical question, actually. And in my opinion, but maybe it is the the opinion of a person using math in order to have convergence guarantees. But I'll focus more on traceability of the result of a training procedure and the transparency in that case, because during the training procedure, maybe we don't know in certain cases what is actually happening there. But what we have as a product, so what is deployed by an algorithm, should be safe and should be transparent and highly explainable. Something that it is not always meet as a requirement. So I would care about more the product that is explainable.
All right. So I just want to kind of test my understanding, formalizing our theoretical understanding of this.
Okay.
First, we outline our theoretical understanding. We test our theoretical understanding. We formalize our theoretical understanding. And then we jump into, okay, what does that theoretical understanding tell us about how we can make real world improvements? Is that how we use the theoretical understanding?
How I am trying to face this the reinforcement learning. So maybe I have some new insight about a new algorithm, but before seeing if it works in practice, I try to at least see if it makes sense from a theoretical perspective. If it is the case, I have maybe also some insight of what can happen in practice, and then I test it in practice. And moreover, when I have something that is working well in theory, then I maybe have some insight on how to enhance the performance in practice in real world applications. So this is my way of working, but I don't know if it's right or not.
No. So are there people in the space that would prefer to jump over theory and into, does this work in the real world or doesn't?
Surely.
And what, like,
surely.
so what are what are the benefits of doing, or what are the drawbacks, I should say, of doing that approach versus starting with theory, proving theory,
And deploy.
and then getting into the real world?
In my opinion, the benefits are that maybe you have an intuition that in practice is working for some reason, and you are just skipping a lot of difficult part that is the theoretical part. So you may have something that is working particularly well in practice, and something that can face also real world scenarios. And instead of going through the theory, etc., etc. I think that theory and practice are two words that are there and that often do not communicate. That's a reality. Yes, I've been at ICML at a workshop about this. It was super interesting, but I am trying to bridging theory and practice. That's my purpose. I know that with this work that I presented today and the other that I'm taking right now, I am more on the theoretical side, but I think that both are important, and having something working super good in theory is super good, and then having something that is also working properly in practice is very important, to have something working well in both the words. Not always is possible, but I do not prefer one or the other. I am trying to understand what I'm doing with the theory, but I also want something that are related to real world requirements, and I want something that is working.
Right. All right. That makes sense to me. Thank you, Alessandro, for taking the time to share your work and to answer my questions. We appreciate it.
Thank you very much, Alison, for having invited me here today. I think that it's an invaluable opportunity for everyone, so I hope that you reach a lot of scientists